have to start over again. Not too interesting. This is an array of 10 zeros. So if you look at this, the data type, you can always access this with the .d type attribute. It's a float 64. So I could if I wanted to. I could specify that I want a 4-bit float. You can various ways to do that. You can say float 32. Or you could say just one character F. This works. And the various there's other simple. You can have an array of 1. Not too interesting, but very useful. You can have an empty array. You know, we're lucky that our empty array came up all zeros. It's not guaranteed to be zeros. You could get all junk. And then another important one is a range of values. So this is like Python's range, except we can start with say 10, 20, and step by a fraction. You can't do with Python's range, but it's the same basic. Works the same basic way as Python's range. And another way to get some numbers like this, instead of specifying start, stop, and step, I could say where I want it to stop, where we want to start, or we want to stop. Those are endpoints inclusive. So one of my numbers is going to be 0, and one of my numbers is going to be guaranteed to be 10. And then I could specify. Then I specify how many I want in between those two numbers. And so I get 9 steps. I get my 0, I get my 10. And then I'm guaranteed to have 1, 2, 3, 4, 5, 6, 7, 8, 9 ones.
That is pretty cool.
So that's those are just basically the simplest kind of arrays we can get. And let's go back to creating a range. Just like a Python array, Python list, I can slice this various ways. I can go from say 2 to 8. Or I can get the whole thing, or I can go get everything except the last array. I can reverse it in the usual Python manner. So the slicing is, in this sense, works exactly like the regular Python slicing you're used to.
Does this have like an identity matrix? Because I noticed your array was
Sure.
it's zeros.
And you can also do, I think you can do upper and lower diagonals. So Python already has actually an array type. It's in the array module, and it's the same type of deal. It's homogeneous and it's contiguous. So what's the big deal here? Well, the big deal is all the operations that Numpy gives you that allow you, that work on these arrays all at once, what they call vectorization. So an example of this is take, say, some mathematical formula, and so what I'm going to do here is I'm going to do the mathematical formula here and see how my tech is. Say, I have to put these. Okay, so I want to take this mathematical formula. Oops. I want to take that mathematical formula and express it in Numpy. Now in Python, it's easy to express this in Python as well. So you could do something like the following in Python. You could say, use a list comprehension. You could say something like math.sign t times math.time. Say that I'm going to give it 32 steps. I'm going to make that gives me that's pretty easy in Python using a list comprehension. But in Numpy it's even easier. What I can do is I can use linspace. So I can say my t values are going to be from 0 to 1 second, and I want 32 steps. And then my y is going to be sine 2 times pi times f times t. Okay, that's all, and that's all I have to do. It did the sign of this array all at once. I didn't have to figure out what my dt was or any of that. Now I can plot that.
But we need F in there, right? Or did you go?
F was defined above.
Okay.
Yeah, so yes, F was defined above. So this is very, very crude looking. We can do more steps. So let's do more steps. So I'll do 512 points. And now we get a nice looking 10 hertz sine wave. So another example of this, I've got my sine wave, so I'm going to take the Fourier transform. The reason I want to do this is the Fourier transform is complex, so I have some complex numbers to take to find out. let's say I want the power of this spectrum. So basically what that is, it's the sum of the square of the reals plus the square of the matrices. See two spikes where my generates are. And that real. So the thing about this is that I don't have to think in terms of for loops in terms of for loops and keeping an array. What my limits are. I can just write things down as I'm thinking them. So those are one-dimensional arrays. So see what the dimensions of an array are. You can look at the shape. This only has one number for the shape, 512. So, again, one way of thinking about this, I'll put a little image here, so it's got like this. Yep.
How does Numpy know, like with your FFT, what the X indices? Does it remember that you had a lid space associated with the Y array?
No, because when you do the Fourier transform, it's just a set of points. You have to go and associate what the bins mean yourself.
So in that case, it assumed the indices were 1, 2, 3, 4, 5, 6, 7.
Yes.
Okay.
Yeah. Zero base, zero,
Okay.
zero through. It's gonna that's complex. So
Right.
it's your negative as well as your positive. But you have to go and tell it, and it gives you some tools for that. What the bins mean as
Okay.
far as frequencies.
Yeah, there's that function to provide the bit values.
Yeah, I don't want to get too much into that, but so I stole this from Carmel, and that's how to load an image here. So I was going to load an image of a three-dimensional array here, and let's see. This is some IPython magic. So the image, I can load an image object and display it. So display is built in, but image, I have to load it from IPython core display. And this is a nice thing about IPython. Right now, I don't remember where that image is, but I can do the following. I can go start looking under my file system. And that's in my home directory. Users, Cook, pictures. So this is IPython doing this. It's allowing me to browse the file system. I think it was called image. So here's a three-dimensional array. Okay. So in NumPy speak, these are the axes, and you can think of them as the axes in geometry. So this would be the first axis, then the second, and then the third. And then So let's create some multi-dimensional arrays. An easy way to create test arrays that I use a lot is using the random.random call. So normally this would be numpy.random.random, and it's random is loaded for us. So, and you can give it the shape of the array you want. So I'll say, say 4, 2, 2. So I get an array here of shape 2 by 4 of just random numbers that you can then use for testing various things. And the shape is 2, 4. I'm not sure why this prints things this way. So the idea here is you can operate on these values in various ways. So let me create another one. I'm going to take a range 10. And now this is a one-dimensional array. 10 elements. I can reshape it into basically any shape that where the shapes multiply up to 10. So let me try 2 of 5. So we'll call this B. Now, there's various ways you can operate on an array like this. For example, what if I want to get a maximum element from B? So there's a max method, but the question is, what do I mean when I say max? If I just say b dot max, what it does is it gives me the largest number of all the elements in there. So essentially what it's doing when you just call max, flattens out the array and then gets you the largest. But what I wanted something different. Let's say I wanted the maximum of each row. The row is axis 0 on the first axis. So I can specify that I want axis 0. Well, actually, different than what I said. This is actually getting the maximum value from each column. So when I said axis 0, it's along this direction. So it's along the direction of the rows. So if I do axis 1, okay, finally that's the maximum value of rows. And I can also specify -1, meaning give it to me from the last axis, whatever that happens to be. And it's that same thing. It's the same as 1. And then you can continue in this and give me the second from the end. And there's only 2. So most calls like this where there's ambiguity of what to do with the multidimensional array will have an axis argument. Same thing with sum. I just call sum, it gives me the sum of all the numbers. Usually not what you want. And that's the sum of columns. And this is the sum of the rows. So it should have been, so if I look at the shape again, so that first axis has 2 elements, and that second axis has 5, which gives you an idea of what it's going to do. For axis 0, it's going to sum the columns, and for axis 1, it's going to sum the rows. Now, there's my A again. We go back to reshape. When we use something that has more than 2 factors, something like so if I want to reshape this, and I don't want to think about the, let's say I want to reshape it and I want it to have 6 rows. So I do not have to specify this second axis. I can just give it a -1, and it will do the right thing. And I continue this way. I could reshape. I want 3 rows, 2 columns, and then I don't know about this last one. So as long as it can find a number that's going to factor into 12, you can do that. Now, if I give it 2, if it doesn't know what to do, obviously that's ambiguous, so I don't complain. So you can only use this once on one of the axes. It comes in really handy. Now I can also do something else here. I had a reshape, let's see, let's try 3 and 4. Okay. But I can also do this. 3 times 4 is 12. I can add a redundant dimension there. You can see you're seeing 3 brackets. And this will come in really handy later when we talk about broadcasting. It's redundant now, but the nice thing about the axis where you only have 1 dimension is that will combine with any other array. You could think of it as multiplying a scalar times an array. It's the same sort of thing. Now let's look at, we didn't talk about, we have this multi-dimensional array, so E. And this is something you don't have in Python. You don't have multi-dimensional arrays in Python. You'd have to do something like, if you wanted to access this in Python, you'd have to say, let's say I wanted to access the 6. So I'd have to say, I want that first row and the first element. But in Numpy, we can access this like that. So this comma allows us to access that directly in the multidimensional array. Now you can combine this with slicing. So I could say, I want to see all of that axis, and I want to see the last element. Okay, so this is the 4 and the 9, the last element in each row, and I can slice into. I can use slicing, so I can say 1, 2, 3. So the comma separates the slices, so each one here has a slice. So I get all of them, a slice from all of them. Yep. Let's go back to the example that we have where we take that and reshape it to say 3, 2, and 2. So now I have a shape like that. Well, let's say that I want to do something like this. I'm only interested in the last element of each along that last dimension. Let's say I don't know, I'm always interested in the last element, but I don't know how many dimensions I'm going to get, how many axes my array has. You can use ellipses. And you can also do that. You can put the ellipses in between. Now, here it's not, doesn't mean much. But if I had, say, 4 dimensions, then that might come in handy. Actually, say you wanted comes in handy. You say you want the first from that axis. You don't know how many axes are in between, then you want the last. And it'll do the right thing for you. So that's actually the only things that Numpy adds to the usual Python slicing, or the comma for multidimensional arrays, and that ellipses. Everything else is the same as it would be in Python. So for example, you could do this, and that means reverse on that last axis. Any other of your Python slicing works there. Okay, I want to talk a little bit about broadcasting, because it's a difficult subject if you go by the documentation. But my basic understanding of broadcasting, what this means is when you have 2 arrays, when can you operate on the array? When can you add them, multiply them, divide them, whatever the operations are, based on their shape. Let's take A and B. Okay. What you can do is you just take those and right one on top of the other. Do they match up anywhere? And in this case, they don't match up anywhere. So you couldn't broadcast these 2. But if I had something like, I took C and reshaped it, which is A reshaped, I can do the -1 trick because I know I want 2 in the last position. Let's try and add to B and C. I think what I want to do instead is Well, you move on. One thing I want to talk about is how do you get data efficiently from some other code you've got. And let's say you've got a large Python list. You want to convert that to a Numpy array. Okay. One way you could do it, you could just use the array constructor. And so now I got a. But you don't want to do this because it's horribly slow. So using array, for something like this, some simple example is fine, but you generally do not want to use it for large arrays, particularly for loading up, say, a large list. What you want to do is instead is create an empty list ahead of time. So I'm going to make it 10,000 elements, and I'm going to d-type something compatible. I can say float for 2. And then I can say copy remember in Python when you use a call like this, it basically means copy from this side to the left hand side. So I can do that. And okay.
What was the data type in your first example? Would it default to float 64?
Well, let's try. Yeah, let's try that. I can use Python types. This may be because I was using the math kernel libraries on the other system. I didn't test it on the other system.
Is it range to range list of walls, or is this converting each list of quotes?
Let me move on to the next example. And that's using drum buffer. So let's say that you're using some C code, and that C code returns some buffer to you in its API. So I can simulate that. Let's say I create a list of integers. 10,000 of them. So this is a C buffer of length 10,000. And then I can use the from buffer column. But I do have to give the type. Now this is to be specific. So that takes microseconds, at least something's working. Okay. So from buffer is a really efficient way to get data to your NumPy array if you've already got it in some kind of contiguous C buffer, which most C APIs are going to give you. Another thing you want to worry about using array again. Let's say I have, you've generated a list of arrays. This sometimes happens that it's easier to create a list of arrays, or you have some list of arrays. So I'll create one that's not very interesting. Again, taking this, turning it into a NumPy array. So each of these subtypes is a NumPy array itself, but it's a list of NumPy arrays. And if I use the array constructor, this might it's much better to use what are called stack calls. So for instance, I can stack them vertically. Should have jumped after that. Okay, I'll do it. Try this again. Make it a little smaller. So I'm going to take these and just stack them vertically. So each one of these becomes a row. Okay. So that takes only 11 milliseconds. And should I risk the other one?
Just check your house.
Yeah, this is, so that's a factor of at least 100. So upshot of that, don't use this array constructor like that for when you're in your program. It's okay for examples. It's okay for small. You want to take you want to create say points, which is an ordered pair. I mean, that's fine. Do not use array on large sets of arrays or lists. Use stacking operations. So that one was VStack. There's also HStack. So I can.
What's the difference?
HStack is columns.
Okay.
VStack is rows. So let's say I wanted to take. Let's say I wanted to create a set of points. So I could take. There's also column stack, which is similar to HStack. I think this is just another name. So I want to set points. So that'll create a set of ordered pairs. And then I can also row stack. And that creates rows. And those are very quick. Now another routine for creating arrays quickly is concatenate, which just concatenates together. And then once you've concatenated, you can reshape how you like. So that's a very quick way of creating arrays from other arrays, concatenating. Now what if you've got, let me go back to, my son. What if you created something like your sine wave? And let me go ahead and take the Fourier transform again. And you want to save that. So, a really simple, easy way to save that is just to use the save call. You know, for explicit. It's numpy.save. And I just give it a file name. Now let me look where I am. That's my present working directory. This is IPython now. I can go around the file system. I'm going to move into my home directory. Just for information, I could also use loads in the NumPy namespace also as NP, and this is very common. You'll see this a lot. This is almost standard when you're importing NumPy. You import it as NP, and then everybody knows what you mean when you say NP. Save. Let's give it a file name. Then I can give it the array. And then I can load it on the. Now what it did is it added an extension .apy. It's a long list. Even more convenient, let's say you have a bunch of arrays that you want to save. So let's say I want to save that sine wave and the FFT. So I can do this. I can say save Z, and then I can give it a list or keywords. I usually like to give keywords. So FT equals FT, and sine. And then when I load it, the same load command works for this as well. Now the extension on here is npz. Look at this, look at see that. I can look at the key. Well, that's nice. Good idea.
You find out the shades that travel the ship. We'll ship
So basically you can access stuff as if it was a dictionary. So I can plot this. So that's and it's platform independent. So you can one thing I'd use this for is, say you have some data together with, let's say you have a config, you have something like this. So this is like, say, .ini format, and I can say say z data. And what does that config look like? It's a array of strings. Just make sure that when you get this, that you say toString. Otherwise the Unicode won't work. So Unicode works. So that's an easy way to save a config along with your data. And last thing is you can also compress it. So I could do the same thing when I get a compressed file. And I should point out that if you don't like that MPZ, open your file first and give it a file object with your name, and it won't add the extension. Okay, next time. Okay, let me try broadcasting. See if I can get this example in there. One thing I want to try here is what I want to do is I want to take that sine wave and I want to make it like a waterfall cascade, so that you have a sine wave, a sine wave, a sine wave, set 45 degrees cascading up the screen. I have my sine. I have my sine wave here. I want to take the sine wave and repeat it, say 10 times. I want to move it up the screen each time. So what I'm going to do is I'm going to take that and I'm going to make points out of it. So I'm going to column stack time points and so column stack once tuple. So this is 512 points with time along the x-axis and amplitude along the y-axis. And then I'm going to create 10 of them. So I'm going to create, we call it waterfall ambitiously. So what I'm going to do, I'm going to create empty array, 10, and then 5, 12, 2. So now what I can do is I can just say this. And then each one of those. So now I've just basically got this repeated 10 times inside here, the sine wave. Now what I want to do is I want to spread it out. So basically what I want is, I want to say, if I do it 45 degrees angle, I want to increase x by 1, y by 1 and x by 1, y by 1 and x by 1 greater each time. So a way to do that would be to say, take a range of 10. I'm going to take 2 of them. I'm going to transpose them. I could also do column stack. Column stack. Column stack creates columns, so it's going to create ordered pairs. Offsets. So you can see it's going to go increase 1, xy, xy, xy each time. Okay, but there's a problem. My waterfall has this shape of 10, 5, 12, and 2. My offsets has a shape of 10 and 2. So I've got 10 of these. You think, can I just add them to the 10 of these and it'll add them in the right place, but it won't work. Because they can't be broadcast together. So what I can do is I can take the offsets, reshape them, okay, now how would I reshape them? Let me write this down. So one has a shape of 10, 5, 12, and 2, and the other has a shape of 10 and 2. So I can broadcast them together if I add a redundant axis on the second. And that's easy. There's a couple ways to do that. One way is to use reshape. there's another way to do that. I can take offsets. Expand the dimensions of offsets along one axis. Leave one will do it. Okay, so what expand dimensions does is adds one dimension along an axis you specify. Now I can say, that works. So how do I look at this? Well, I have a series of I have 10, oops. I have 10 of them. So I'm going to plot 10 of them. Now, the plot, it likes X and Y separate. I've done them as points, so here's the way I would do that. I take each curve, and for each of those points in there, those ordered pairs, X is 0, so I'm saying everything else up to the last axis, then give me the 0. And then this is the Y. That's an example of broadcasting by adding a redundant dimension. And actually, I do use this to create waterfalls, not like that. The format of waterfalls, actually, matplotlib, you can do it in three-dimensional waterfall plots. Didn't talk about how to do fancy indexing. This is essentially sort of like NumPy's version of pointer arithmetic. So, see, I had, going back to 8 range 10 here. And take this, and you can index it by using an array itself. So I can say I want, out of this, I want to pick out 1, 5, it just happen to be the indexes is happen to be the same as the numbers. And so you can do things like with this, like you could ask for the non-zero elements of that. You can say, I want to index by that instead of non-zero elements. So do it just from here. It's the same. They look a little too similar. Okay. So that's, and you can do multi-dimensional. That's pretty simple. One thing you do have to know is that it's actually faster for some reason to use the take method, which accepts the same type of thing. It's just, basically this should be equivalent. A.take147 should be the same as A147. But for some reason take is a lot faster. So You've got to, you're doing this in the inner loop, use the take method. And avoid directly using arrays for indexing, like fancy indexing like that. Now you can also do booleans. So you can have arrays of booleans. For example, one way of creating an array of booleans is to say, what values in A are greater than 5? So first 6 are false, and the last 4 are true. And I can pass this on to A, get back. And you can do logical combinations. Now you can't use Python OR, it doesn't work. So it's not quite as nice as it could be. So I get everything that's less than 3 or greater than 7.
Does take accept these things?
No, take doesn't accept booleans, but this boolean seems that the boolean action passing a boolean is as fast as it can go. It doesn't get, there's no faster way to do it, but it's fairly efficient. Maybe a really large boolean